Next, I'd like to talk about Grignard reactions. Grignard reactions are very important because they involve the joining of carbon chains, and any reactions that allow the joining of carbon chains are very important in organic chemistry. Now, the reagent we use is called the Grignard reagent, and what it is it's a reagent that's made by inserting a magnesium between a carbon and a bromine in an alkyl halide. So in this example here, what's happened is that we've got a CBr bond and the Mg has plonked in between the C and the Br, forming the MgBr compound. The Germans call this concept Umpelung, and that's a funny way of saying reversing charge. So what's happening is that we've got a delta minus on here and we've got a delta plus on this C right here. And then if we throw in magnesium, we have now got a magnesium here connected to a bromine. So the Mg has inserted itself in between this C and this Br. And as we know, metals are electropositive and tend to have delta plus charges on them, which means that whatever they're connected to will have a delta minus charge. But effectively, just like we did with the sodium borohydride, we can think of these things without the magnesium and just put a negative charge on the C to which the magnesium is attached. And just go ahead and automatically turn the Grignard reagent into that kind of species. Take a look at the pattern as I've got it over here on the slide. I've got an MgBr here. I remove the MgBr and I put the negative charge on the C to which the magnesium was attached, and you can see it right there. A common mistake is people will see something like this with the MgBr and they'll say, okay, I know what that looks like. That's going to be the same as this. And their thought is that there's a carbon atom right here, but there is no carbon atom right there. What this is a magnesium connected to this carbon. So this is not the negative charge here, the negative charge is over here, connected to the C to which the magnesium was attached. And we can see that pattern bearing itself out here as well. MgBr, negative charge, will end up here. MgBr, negative charge, ends up here. MgBr, negative charge, ends up here. The negative charge always ends up on the carbon to which the magnesium was originally attached. Right, let's look at an example of a Grignard reaction and show the mechanism. Right, so I've got one started over here. Here is our Grignard reagent. Again, this is a two-step process, so we need to do whatever here is required with the number 1 first before we use the number 2. We are not allowed to touch this H+ until we have finished working with the Grignard reagent. So looking at this one, the Grignard reagent itself, we remove the Mg and put the negative charge on the carbon to which the magnesium was attached. There's the carbon right there. Now what we're going to do is, again, we recognize that we have a delta plus and a delta minus on this system right here. I won't put those on, but we know that the negative charge will be attracted to this carbon. So we know that a new bond will form between this C and this C here that's making up the C double bond O. Just like in the last case with borohydride reduction, we can't just form a new bond here because that would give 5 bonds on this carbon. So what's going to happen is the electrons will be pushed up onto the oxygen. So here's what our new structure looks like after we've added in the Grignard reagent. Now I'll leave the C there. That's the C that had the negative charge on it in the Grignard reagent. And you can see what we've got here is a new bond. A common mistake that people make at this point is instead of forming a new bond, they just go ahead and plonk the C right in here. And what that has actually done is shorted a carbon out of this structure. So we don't want to ever do anything like that. Alright, so we formed this new bond and we've got our structure here. And now what we're going to do is we can do our second step, and that is add in the H+. And again, when we're doing the arrow comes from the negative and goes towards the positive to form the new bond. And that's showing how we're getting a new bond between the O and the H. So here's our new structure. Try and draw it the same way. And there we go. There's the new bond right there. And there was the C that had the negative charge originally. Alright, so that's the mechanism. As I said earlier, the big mistake that people make is fusing this carbon with this carbon, so just try and avoid doing that. Always make sure you form the nice new bond that I was talking about earlier. Now, whenever you see a Grignard reaction, it can actually be expressed in two ways. You can have the aldehyde or ketone out the front and then react it with the Grignard reagent, or you can start with the Grignard reagent and have the aldehyde or ketone above the arrow. The way I like to think of it is it's like making scrambled eggs. You can add milk to eggs, or you can add eggs to milk. In the end, you're still going to get scrambled eggs. The reason for that is because when we do mechanisms, and I've got that expressed here, you'll notice the first thing I did was I drew this here, and then I drew whatever was beside the number 1 and I put it underneath. Now, had I had this the other way around, the result would have been exactly the same. So I would have had the MgBr out the front here, and then above the arrow I would have had my ketone. And I want you to realize that my first instinct would have been to draw this first and then to draw this above it. And it would have been exactly the same. So having the Grignard reagent out the front or the ketone above the number 1 is going to be the same thing. Right, let's go back to that slide. There's something else I wanted to mention about it. Depending upon the kind of aldehyde or ketone we start with, we're going to end up with a certain kind of alcohol. So if we start off with this aldehyde, this is a special aldehyde because it's got 2 hydrogens connected to the C, we're going to end up with a primary alcohol after we react it with a Grignard reagent. The 2 hydrogens connected to the C with the OH are the original hydrogens that were connected to this C. So what's happening is that we are getting an alcohol group on the end of the compound. Alright, so the net effect of this would be an example. So looking at the mechanism, puts a negative charge here, it adds here, And I'll actually leave the hydrogens on here while I'm doing this. And there they are. And here is the Grignard reagent that we initially started with. And this negative is forming a new bond, and there's the new bond right there. We add in the H plus in the second step, and we get our alcohol. But not just any alcohol, a primary alcohol. And remember, primary alcohols are defined as being the OH, having the OH on the end of the chain. Another way of looking at it, a primary alcohol is one carbon connected to the C with the OH, and there it is right there. Alright, let's take a look at a secondary alcohol, and that would be formed from another aldehyde other than formaldehyde. So let's say we started with this one. So now we only have one hydrogen attached to the aldehyde. We'll pick another Grignard reagent, say this one. So there's our Grignard reagent. Again, look at the pattern. We take the Mg off and we put the negative charge on the C to which the magnesium was attached. You can see the new bond right here. And the new bond forms between this C and the C that made up the C double bond O. And as you can see, we are going to obtain an alcohol where the OH is in the middle of a chain. The other way of looking at a secondary alcohol is that it has two carbons attached to the C with the OH. Here's the C with the OH, two carbons attached, one here and one here. So that makes it secondary. Alright, let's take a look at a ketone, starting with a ketone. Now ketones have two carbons attached to the C double bond O. We'll use that as our Grignard reagent. Again, we take off the magnesium, we put the negative charge on the C to which the magnesium was attached. We're going to get a new bond between this C and the C double bond O. And there's our new bond right here. And then we join the H plus onto the negative charge. And we'll get our product. And this product is a tertiary alcohol. And the reason it's tertiary is because we now have three C's connected to the C with the OH on it. 1, 2, 3 C's. And that makes it tertiary. So as you can see, depending on the starting material, whether it's formaldehyde, an aldehyde, or a ketone, we can end up with a different kind of alcohol, a primary, secondary, and tertiary respectively.